is you have some figures maybe made by others or by yourself in the past, and you do not have easy access to the data that was used to make those figures, but you now have a new data that you want to show on those figures. So for example, in this paper by Leonel Romero, let's say there's a figure here that I'll be using as an example. This is a figure for lambda of c, which is length of breaking front. And there are many studies, like if you go to the Sutherland's paper, so this figure was actually gotten from another paper that assembled several other measurements that were done, and then just to compare his own measurement to what other people did in the past, or rather to collate these measurements together in a single one panel. So say for example, it could be anything, it doesn't have to be this particular one, it could be any figure at all. This code will work with any figure. And I'm going to explain what the code does just in a bit. But say you have a figure that looks like this, and now you have your own data and you want to plot it on this data. The data again is corresponding to the same thing here. So in this case, you have some lambda, so the breaking front and the speed in the x-axis. And you have now recently made your measurement. You want to plot it and compare to like what other people have in the field. Does that make sense? What other people have in the field? Where does your measurement field for? Maybe to help you further interpret your result or make some discussion of how your data relate to what other people found in the past. The first step is you want to have maybe PNG or any image format. So to do that, you just do a screenshot. So I just do on Mac, we just need to do hold the command shift and 4, and then it gives you this sort of interface where you could like screenshot. So now I've screenshot the image. So this is the image that I just screenshot. It has saved. And so now let's go to it has saved, and I've given it a proper name. Now let's write the code to do that. So let's get straight into the code. Now that you have understood what I want to do, again, what I want to do is you have some existing figures. It could be from you, it could be from the literature. As I've shown you how to do a screenshot, get a screenshot, and you load that screenshot, and then you plot your data back on top of that screenshot. So that's basically what you're trying to do here. So I'm going to call this particular project overlay a new data onto existing figure, which could be from screenshot. All right, so first we'll start with the import. We'll start with the basic import. I think you're already familiar with this. I'm not going to waste time here. We're importing about 5 of the packages. This one is just to save the data so that in the future, if we have already calibrated this figure, we shouldn't be calibrating it again. So anytime we have new data, we could just load this information and plot it since we're calibrated. So it's just kind of like calibrate once, save the information in a Java or JSON, kind of like Java type file. This one is for files, so extracting certain paths to extracting those images, creating new folders, making stuff more automatic. This one is for doing most of the operation, like calibrating the image, and this one is for the plotting of the image, and this one is for the loading of the image. So those are the basic stuff that we have there. And so let's do some little housekeeping. But before that, I want to define a function because I want this to be added to my toolbox. I want this particular project to be as a function. So it to be a single function, and that's the function I'm defining here. Again, on this channel, I hope to do very useful tools like this that you could also develop your own toolbox and just put this function there, and then you import and you could use it anywhere on your computer easily. So basically, that's the big idea. So it will be a single package library at the end of the day on image processing that will have all these two in them. So while I'm designing that toolbox, I want to walk you through the entire process, and that's exactly what I'm doing here. So this function, again, you could change it to be very short and simple, but again, I'm just keeping it so that everybody can understand since I intend sharing the code together. So I'm going to call this particular function again def is how you define your function, and the name for the function is overlay data on figure, which is basically what this function is going to do. And as taking in input, it's going to take in the path to where that screenshot that we just made from that paper. We just open a paper anywhere on the web, make a screenshot of the figure that you have data similar to, save it in the path, and then you're going to provide a path here. And then we're also going to provide our new X. I'm going to explain all this, provide our new Y, and then provide the scale, whether it's a linear scale, like the axis of the figure that you're screenshotting, whether it's linear or log or whatever, you're going to provide a value keyword here. By default, it's going to be linear. Again, it just ensures that your data is also like replotted. And so if, for example, if the figure you screenshot was a log plot, then your data, if you could just provide this for it and it's able to automatically plot it as a log plot, basically. And then for the calibration, 4 point is sufficient by default, so I'm setting 4. So basically click 2 points on the x-axis, 2 point on the y-axis, and you provide the physical value corresponding to those. I'll show you that. I'm going to demo everything, and then it calibrates that. And if calibration is equal to 2, true, it basically calibrate the figure and save the data. If it's false, by default, we're leaving as true because we're assuming that anytime you're using this function, you are having a new figure that you want to actually calibrate before showing the data. But say you have already run this particular script or call this function on a particular figure before, then that you have another stuff that I will show you later that will automatically save this information, so you don't have to just so you are more efficient. So it saves the calibration information. So the next time you want to use the same figure, so you have to want to add new data on top figure that you've used in the past, then you don't have to calibrate again. You just load that data automatically. So that time you have to just set this to be false. So it doesn't calibrate, but it loads. So if you set this as false, then it's going to look for this calibration file. By default, it's none, but if you have saved it before, they have to just provide where you save that calibration information to. And then the output path, by default, is none, but that's assuming that you don't want to save the output. But say you want to save it, then you just have to adjust that to be some value. Okay. And then the other key line arguments, these are just for the line type, the line size, the width, the color, and stuff about plotting. Great, so now we have defined our function. Let's go straight into making things happen. So a little doc string, this is just like a little documentation for the function that helps other people that are using it to understand what this function does. So if they don't know how to use this function, and if they do help and they call this name of the function, this is what gets printed to them. So basically summarizing what this function does, or whatever this tool does, it overlays a new XY data, which is your own data that you've gotten that you want to plot on existing figure. So it overlays that new data on top of existing figure, which could be just any screenshot. I mean, any screenshot at all. And then the input, the key parameters that you have to take into consideration before using this package is the Boolean. You want to check whether you want to calibrate it or not. It could be true. If it's true, it means you're going to have some interactive sort of click and input stuff where you calibrate the figure, or if it's false, then it just loads the calibration file information as I explained earlier. And the calibration file basically is some information saved in a JSON file. So that's the doc string. And first, let's do some housekeeping. By default, we could define the line types and stuff. So for example, I'm giving it by default some magenta as the color of the line. So our new data that we're plotting on any figure, it will show as magenta. I choose this color because it's one of those few colors that not everybody use. So assuming the figure you have don't have magenta, then your new line will show as magenta. If I use black, many of the plus uses already black, so I don't want to use black. That's why I choose some color that is rare, that is not very much used. And the line type, you could set it to be anything. You could set it to be 4, you could set it to be whatever. You want it to be big, so you could easily see what you're showing. Okay. For the calibration file, we want to check for that. So for example, if someone don't know what they're saying and say, yeah, I already have a calibration file, then you want to quickly, before running through the script, you want to do some checks. So you want to look for the calibration file. Is it provided? If it's not provided, then you have to give them some useful error message. And this is how you provide it. You just use the raised error, and then you have to tell them you must provide the calibration file. Then okay. Then they'll go back to the doc string and then read what that means and then provide a path. So these are just housekeeping. The next one is they're providing some X and Y values. This is their data, the X and Y, what they want to plot on the plot, the X values and Y values. basically, but it could be in anything. It could be some people could provide that slate, some people could provide that whatever. So you want to convert that to some array, so it's easier to visualize. So that's the first step. We just convert those and make sure it's a float, and then just housekeeping so that everything runs smoothly. Okay. And then the next step that we want to do is to create a transform function. This transform function basically ensures that what data they have and whatever it's already on the axis of the figures that they got as screenshot is the same. So basically, it's transforming it from linear space to log space. So suppose the screenshot was in log space, but their data is in linear space. But then by telling us that their data was in the figure is in log space, we transform that to log space. So but if they already provide the log scale, then we don't do anything. That's just what this section is doing for us. Now that we have done most of the housekeeping, we have to load the image. So basically, it's a path to the screenshot, which we're going to give as input to this function there, as I said earlier. And so, yeah, I could also use, somebody could ask, why are you not using OpenCV to read this image? Why are you not using a scikit image? Why are you not using P? Why are you not using any other package? I mean, this is Python. Why are you not using the popular one? Why are you using Matplotlib of all packages? Well, Matplotlib also has a read im that you could use, so it doesn't matter. You could use it. You could use anyone, but since we're using Matplotlib to plot stuff here, I want to stick to Matplotlib. And since it's like they started visualizing too, then I want to like keep to it. It's almost everybody that uses Python has this particular package, so I don't want something that people will struggle with. So I hope that makes sense. So I'm just using Matplotlib to read in. So I just provide a path, and then this will load the image exactly the way it is. If it's a color image, it will load it as a color image. And we have this image as the variable loaded. Next step is we want to calibrate this information. I'll walk you through chunk by chunk. I wouldn't go line by line so that will go fast, but this step is just calibrating your image, basically just what you have to do. You first of all check if you have provided a calibration file. If you have provided a calibration file, then it will be able to jump over. If you have not, then it will definitely force you to do these steps. And so first is plot the image. So all these places just plotting the image that we just loaded here, and then making it clickable. Basically, it's plotting it and shooting it back to you, so you're able to click. I'm going to run all this and then walk you through everything, but I just want to walk you through this before. So when I run it, then we just go through step by step of how to use it. But this is just what is in the code. I just want to make you familiar with the code. So basically, this step is like plotting the image, displaying it back to you, asking you to click 4 points. And basically, you click those 4 points, and then the next step is basically asking you to, for each of those 4 points you clicked, provide the physical values corresponding to them. And once you have provided that, then it automatically remaps in this next section here. So in this next section, the first section we did about the calibration mode. Once you are done with that, the next section is it remaps. So everything here is just remapping those information. So basically moving it from the pixel, which is what the image is being loaded at, and using the physical information you provide to map the pixel to physical. So everything is physical. So that once you provide your data in physical space, it's able to get that. And towards the end here, it's just saving the calibration information in JSON file, which I said earlier, so that anytime you want to reuse this same screenshot that you're operating on here, you could just easily load it, So it's just a way of being more efficient. So that's all that was in that section. In the next section is the replay mode, what I call the replay mode. So it just handles what if the person already have a calibration file. Basically, it just loads the calibration file. It just opens the calibration file and extract the 4 points that it clicked and provided the physical minutes on, and then it refresh the brain and provide it to the program, so you are good to go. So you don't have to do any click and input to stop again. It just loads and you're good to go. And then the next step is to clip the new data. So suppose your data, rather than the figure, it's just going from some extent, going from 2 to 10 and your new data, because you did new experiment and you use some maybe broadband measurement that it's able to go from negative some values to 1000, then I mean if you want to compare onto this figure, then you want to just show the portion that corresponds to the range of that figure. Does that make sense? So you just want to compare 1 to 1, basically the same range. So that's what this portion of the code is doing. It's just creating a mask. And again, the mask is based on those points that you click. So we'll click on the edges, on the ticks, on the mark tick X and Y ticks points. And by that, it could be able to like tell the program is able to know from those points that you provided, from the clicks, to tell you the extent that you have the data on that screenshot on. I'm going to demonstrate all those things, but don't overstress yourself at this point. Just know that this portion of the code is just ensuring that you don't plot your new data outside the range of the data you have on your figure. That's just what. And then in the next step is to plot stuff back onto that image. So here you're just plotting the final stuff back onto the image. And here is just how to call it. So here it finishes, and then you have access to the fig and the fig access, but it also saves the figure to some output. So this is how to use the function. Here's just an example of how to use the function. That screenshot that I took, or in fact, even before taking that screenshot, since I needed some information to work on, I generated some synthetic data, which are from here. So it's just some data that will take some shape similar to the plot that I showed you earlier on. So I just generated this just some random data. You don't have to generate random data. If you already have your data, then this is just some noise adding to some sort of scaling that I just made up. And at the end of the day, you have some figures. So if I run this, it's going to like make a plot. So this is the sort of plot. The 6 to the 6, I will show you this line on that figure after I've cropped. Notice that my data is going all the way to 10 to negative 200 because I'm just generating this stuff, so I have ability to generate a wide range. Even though the figure that I was showing you to stop somewhere here at 10 to the negative 11 or so. So I'll be showing you only this portion of the plot, for example, will have the ability. And now this allows me to test the mask that I'm doing. That when I'm plotting it, comparing to that figure, since the figure doesn't go all the way to this range, it should only show the data, my data, which is this blue line, only for that range that you have in that figure. I hope that makes sense. But this is the data I generated. I just generated data that goes outside the range of the example I want to show you. And I've saved this information, the X and Y corresponding to this line. I've generated that data. I saved it in a folder called data. And the screenshot that I took earlier, I saved it as this name, which is just Sunderland Melville 2013. That's the owner of the data, even though the screenshot was taken from Romero's paper. So it's a PNG, it's an image. The data is saved here as CSV. So you could open this and look at this, just a column of X and Y with the data. So basically here I'm using the MP load text to load the CSV file. The delimiter is a comma, and unpack is true. So at the end of the day, I'm going to have my X and Y, which is my data, basically, which I generated from the script gen synthetic data, which I showed you earlier. And because you need this X and Y when you're calling the function, that's why. So remember, I showed you, I'll tell you what the new X and new Y. This is just your data, basically, and this is the data we loaded here. We're supplying it here. So first, we gave the screenshot path, which is the screenshot we took, which is in the data and the image. And then the scale is a log. Remember the figure I showed you is a log scale. So we're telling this a log scale. And then we're putting the calibration here. And to be false, we're saying we don't have the calibration file, basically. If you already have the calibration file, I want to change this to true. Because I want to walk you through step by step of everything. And the calibration file output, this is where we want to save it. So if you don't have it and you want to save it, this is where you save it. Or if you already have it, you also provide this information, basically. So this way to read, or here, this is where to save the information. And then the output, this is what the final output should be called, that overlay result. So basically in this one, it will be this screenshot that we took with your own data, which is this, plotted back on it. And then you could, again, we already provided default if you don't provide this to this way. We'll change that to 4. And this is the magenta. You could use any other color. You could use purple, you could use lime, you could use whatever color you want. But this it's good to use a very rare color so that your color of your line don't match the color already on the data. So you could easily see what you're plotting. Okay, now that I've walked you through, so that's the entire script. Now we're going to run it now and see what happens. So, right. So we'll want to tell it to calibrate. So if you want it to calibrate, you just have to set that as true. So I'm going to save that and then I'm going to run that again. So if you run it for the first time, so you don't have any calibration stuff, this is how it will pop out. It will tell you to click. Again, just read the information on the title of the figure. Again, this is the exact screenshot that I did at the beginning of this video without any of my new data plotted on. I just loaded that figure and it's asking me to click 4 points along the axis. So I'm going to click one where I see this tick. So where I have values easily to interpret. So I have value here, I have value here, and this value is that value. If I click, it should show a red. So that's the red. You want to be as close as possible to the tick. So you click on there. Again, there's a little offset away from it, but that offset almost matches this offset. So that will take care of those errors. On this axis too, you want to click 2 points that you know the tick. So I know this 10 to the something. I'm going to click it here. So it's on that. And then I also need 10 here. So I'm going to click that value there. So now I've clicked the 4 points. After you've clicked the 4 points, if you look here, it will be asking you now to improve. So for the first point you click, which was this point, it's not asking us to provide the X corresponding to that. So now I'm going to take down that figure for a Y. But maybe I should bring up that figure. I don't know whether you'll be able to see that figure, but I already know that the first point that I clicked, just to make the video a little bit faster, was 0.1. That was the X value. And in the Y value corresponding to that point was 1e raised to the power of 8. And the second point I clicked in the X was 10. And in the Y was still that value. And then the third point was along the Y axis, and the value was 1e. Okay, for the X, the value at that point was 0.08. And in the Y was 1e, which is basically 10 raised to the power of -7. And the last point I clicked on the X was still the same point, which is the beginning of my data on that screenshot, which is 0.08. And in the Y was 10, which was 10 raised to the power of 1. And now, if you have done that successfully, then you're going to get this sort of figure. So now it has plotted the data I generated. Again, notice how it's not showing all the extent. All the data was going to tend to the -200. Everything has been cropped because we provided that. So, yeah. So we're just comparing here. And we could see how much our new data, which is shown here in purple or magenta, compares to the existing data that I took from that paper. So this is how you use the program. Again, I just wrote this and I hope this will be very useful to many scientists and engineers and researchers out there who may want to compare their data to existing plots, which could be from them or other researchers. Please like and subscribe if you found this helpful, and also you could drop a comment on what challenge you have that you may want me to make a video on, like whatever project you may want me to see me make a video on. That I will read through and consider most of those stuff. Thank you. Hope this was helpful. And you could just test the code for yourself. Bye bye. See you in my next video.